All right, today we're going to be looking at inverse functions. So we're going to do a little bit of review, see what you might remember from a previous course. All right, so what are inverse functions? Let's start by looking at y equals x squared. Oh my goodness. That's not bad. Okay, so we have y equals x squared. Okay, and if you were asked what do you remember about inverse functions, a lot of times students will say you switch the x and y, which is correct. Some will say there's symmetry along the line y equals x. Yep, that's correct too. All right, so we've got y equals x squared. Okay, if we thought about y equals x and where that falls, something like this, and if we were to fold along y equals x, okay, then we're going to get a graph that is opening on its side, a parabola that's opening on its side like this. Okay, so what's the equation of that inverse function? Well, we just switched the x and y, so the name of this equation, the inverse graph, is y equals x squared. X equals y squared. That's all we did, switch the x and the y. All right, some of the topics that are going to be addressed in this lesson are topics such as our inverse graphs functions. Well, you can see that y equals x squared is a function. It passes the vertical line test. However, its inverse graph is not a function because it fails the vertical line test. Okay, so that's one of the topics we're going to be talking about. All right, so we see symmetry along the line y equals x. Got it. Something else you might remember is you can look at individual points and switch those. For example, if I thought about the point 2, 4, when x is 2 and you square it and you get 4, okay, if I were to label it, okay, if I were to actually switch that particular point, okay, and make the ordered pair be 4, 2, okay, and plotted that, okay, it's going to follow along. Here's 4, okay, and here's 2. Okay, and this was 2, and this was 4. Anyway, that ordered pair, 4, 2, if I were to name it over here, falls on the inverse graph. All right, so those are some things you may remember. So just recapping, the original y equals x squared is a function. However, its inverse graph is not a function. So I wouldn't call that an inverse function like the topic of the notes suggest. Just thinking about this graph for just a second, if I were to restrict y equals x squared, if I were to restrict its domain to be just say all x values greater than or equal to 0, then I'm talking about just this part of the graph right here, y equals x squared, this part that falls in quadrant 1. Well, if that's the only part that I were to reflect, okay, along y equals x, or if that's the only part of the y equals x squared graph that I took every ordered pair and I switched the x and y coordinates and plotted them, okay, then I would only get this branch right here on x equals y squared. And in that case, this restricted y equals x squared would be a function, and so would its inverse graph be a function if I took away this branch right here by restricting the left branch on the original function. So those are kind of things that we're going to be looking at too, or at least be aware of. Let's look at another example. Okay. You may recognize y equals x cubed. Okay, and it comes up something like this and heads up that way. It's always increasing on its entire domain. Okay, I could go through and choose some points. For example, I could choose the ordered pair 2, and when I cube 2, I'd get 8. Okay, I could choose another one. I could choose 3, 27. That's a pretty steep point. I could choose x to be 1, so y would also be 1, so maybe that ordered pair is somewhere down here, 1, 1. Okay, I could even choose something over here like negative 1, negative 1. Okay, and I could choose something like this right here, negative 2, when x is negative 2, and I cube it, I'm going to get negative 8. Anyway, we're working with y equals x cubed. Y equals x cubed. If we're interested in its inverse graph, okay, if you wanted to think about the line y equals x, okay, and draw its reflection through y equals x, it might go, oops, sorry, that's going to kind of continually go down like that. Something like this, and then something like that. All right, so I'm back. I kind of cleaned it up for you. Anyway, here we have y equals x cubed, and so what's the name of the inverse graph? And it's actually a function. Well, we'd switch the x and y, so where y is, we'd replace it with x, and where x is, we'd replace it with y. An easy enough thing. Now, a little problem here that we'll be addressing in this lesson also is we want the equation for the inverse to be solved for y. We'll deal with that a little bit later. Anyway, so now looking at some points that fall along the inverse function. Okay, it's not just simply a graph. We can be more specific and call it an inverse function. If 2, 8 belongs to y equals x cubed, then 8, 2 would belong to the inverse function. So maybe that would be somewhere about right here. Okay, because these points have to lay on top of each other when we fold along y equals x. Okay, so yeah, and you could just kind of look at the inverse point here too. Maybe if this is -2, -8, then perhaps this point here is going to be -8, -2. My graph is kind of distorted, so it's not really a good scaling, but hopefully you get the idea and you remember a little bit about this topic. All right, so if you scroll down a little bit, I've kind of summarized down here some of the things that we've talked about. Numerically, we interchange the coordinates. xy goes to yx from a function to its inverse. Graphically, we have symmetry with the function, the original function, and its inverse along the line y equals x. This notation right here, you can probably see it. It's f to the -1. Okay, that's just a way of saying that we're dealing with the inverse function. Okay, if indeed we have an inverse function and not an inverse graph. But anyway, that's just notation that's used to represent or name an inverse. All right, analytically, the composition, which we covered in a previous lesson, when we put f inside f inverse or f inverse inside f, the result of performing that composition results in us getting an answer of x. Either way we go. So if we have inverse functions and you do the two compositions, the final answer should be x for both answers. Okay, here's some additional information we'll look at in a little bit too. Horizontal line test. If every horizontal line intersects the graph of a function at most once, then the inverse graph is also a function, meaning it passes the vertical line test. So let's look at that graphically back up here in our first two examples. So if every horizontal line intersects the graph of a function, so think of y equals x squared, which is a function, and think of a horizontal line test. Well, the horizontal line test fails. Okay, I don't intersect this parabola at most once. And what that's saying is because I don't intersect this in just one point along the whole graph, that when I fold along y equals x, the inverse is going to fail the vertical line test. Okay, so look over here at y equals x cubed. It was in black here. Every horizontal line intersects y equals x cubed in at most one point. So when you flip that and form the inverse graph would pass the vertical line test. And a specific name for a function that passes the horizontal line test is that function is 1-to-1. That's all this means. So y equals x squared is a 1-to-1 function because it passes the horizontal line test. I just lied to you. Y equals x squared is not a 1-to-1 function because it fails the horizontal line test. But the y equals x cubed does pass the horizontal line test, so the y equals x cubed graph is a 1-to-1 function, meaning its inverse is also a function. All right, so some of the things that we're going to do within this topic would be this. Find the inverse function informally. Well, actually, we're going to find it formally. Okay. And then after we find the inverse function formally, we're going to verify that it is that we do have inverses by performing these two compositions. All right, so first example. Okay, we have to be given a function first. All right, so we're going to deal with f of x equals 1/5 x. All right, well, that's just a straight line. So the visual on that this is a one-to-one function, because any straight line, okay, is going to pass the horizontal line test. So its reflection along y equals x, its inverse graph, will be specifically a function. So we know that to be true, we just have to verify it. So anyway, let's find the inverse function informally. So this is what we did. We replaced y, which is represented by f of x. We replaced y with x. So we're on our journey to find an equation for the inverse function. And then we had 1/5 y. And then what we did is we solved for the new y. So that would require multiplying both sides of this equation by 5, because 5 times 1/5 gives just y. So without showing that, I'm just going to say we multiplied both sides by 5. So the inverse is 5x. Okay, I'm going to trade sides, put the y on the left. Okay, well, I don't want to call this y and then that equation also y, so we use the notation where this y is for the inverse, f to the negative 1. So we found the inverse function. We switched the x and y, we solved for the new y, and we got the inverse function. All right, well, let's verify that they're inverses by performing these two compositions. So I guess the first one I'm going to do is this one right here. All right, so I'm trying to prove that the result of this composition is x. So I'm going to locate the inverse function, which is 5x, and I'm going to put it inside of the f function. Well, the f function is, this is equal to 1/5 of x. Okay, well, wherever we see x, we replace it with 5x. So 5x goes in for x up here. So let's simplify it. And we know 1/5 of 5 is 1, so we do get x. Now that's half our work. Let's come over here and put the f function inside the inverse function. And see if we get x. So let's find the f of x function, which is 1/5 x, and we're going to put it in for this x down here, the outer function, 5x. So 5, that's the outside function, holding a spot for x, and we're going to dump in 1/5 x. Cleaning this up, we do get x. All right, in just a little bit, we'll look at finding inverses by performing this the same set of steps. But for right now, we're just going to leave this topic. Okay. All right. The next thing is to show algebraically that two given functions are inverses. We won't have to find one. We're going to be given two equations and asked to show that they are indeed inverses. All right, so thinking you recognize these two equations, okay, from up above, maybe. We didn't specifically go through and solve this by cube rooting both sides, but we could have. All right, take note of this. Show algebraically that f and g are inverses. So all of a sudden they switch gears here, and they're calling g the inverse. Sometimes that's better because f to the negative 1 and f can get confusing. There's too many f's. So sometimes we give the inverse function a different lettered name. All right, so how do we show algebraically? What do these directions mean without that telling us specifically what to do? Well, to show algebraically that two functions are inverses, it means perform these two compositions. Put g inside of f, see if you get x, and then put f inside of g and see if you also get x, the identity function, the line of symmetry, if you will. All right, so we have our work cut out for us. Guess I'll do f of g of x first. All right, so I'm going to put g inside of f. That means I'm going to take this equation and put it inside, replace this x, and then cube what I put in for x. So kind of building the framework here. I'm ready to dump in for x a new function. Well, cubing a cube root, that undoes that operation. And so we're left with what's underneath the radical, and that happens to be x. Halfway there. So now let's do the other composition, g of f of x. Okay, let's go back to our equations. F is now the inside function, and g is the outside function. So I'm going to build the outside function, the cube root, but where x is, I'm going to replace it with x cubed. Cubing an x cubed results in simplifying down to just x. So we just showed algebraically by two compositions that f and g are inverses. All right, so we're going to go back and call this example 1 because we're going to do one more example. I think you probably get the idea of what we're doing. What we might eventually get hung up with is the algebra. All right. Same directions. Let's show algebraically that these two equations are inverses by performing two compositions. All right, so we're dealing with the square root graph, shifted right 4, and we're saying that g, the parabola x squared plus 4, defined where x is greater than 0, is the inverse. And think about this for just a second. Why do we have to restrict g to be only one side of the parabola? Well, that's because the square root graph is just one side of a reflected parabola. So in order for this to be true, that these are inverses, we have to restrict and only choose one side of this parabola. So really, what is the point of this? Well, just reminding us that, that we want to make that restriction. Otherwise, mathematically, it's not going to have any effect. You'll see. X greater than or equal to 0 is not going to have any effect in our work. All right, two compositions. It's just kind of common practice to start with this one. All right, g goes inside, substitutes in for this x inside of f, so I'll build the framework. Okay, where x is, I'll be replacing that, and the rest of f has a -4. So where g is, or what g is, goes in here. Go ahead and bring down f of g of x every time. All right, the parentheses aren't serving any purpose here, so you can kind of release them, and once you do, you could see then that you're going to cancel these 4's, and you're left with the square root of x squared. The last step is to simplify, and that's going to be equal to x. G of f of x. This square root goes in 4, substitutes in for that x. So the outside function, x squared plus 4. But the f function is going to substitute in for x. Again, every time, bring this notation down. It's organization. Square root, you're going to have x minus 4 plus 4. The 4's will cancel, and we end up with the identity function as it's called. All right, we just showed algebraically that f and g are inverses. So we have a little more work to do, and we're going to do that in the next video.